Good afternoon, everyone. I'm Lakshman Srinivasan, a third year PhD student at IPVF in collaboration with PICM, and my supervisors are Kareem and Pereroka. And my PhD topic is on reactive sputtering deposition of semiconductors like gallium nitride thin films on silicon substrates. Okay, we'll dive into the material itself, gallium nitride. It's an important semiconductor which has its applications on wide range, starting from power devices, transistors, RF components, lasers, LEDs, and even used as window layers in 3.5 solar cells. If you focus on the growth process of gallium nitride, conventionally it is grown by two methods, MOCVD and MBE, which are metal organic chemical vapor deposition and molecular beam epitaxy. I won't elaborate much on this, but it's just that these processing techniques use high temperatures, which is more than 700 degrees. And if we focus on heteroepitaxy of gallium nitride on silicon substrates, then at these high temperatures, after the growth, while cooling down, the large thermal expansion coefficient difference between the thin film and the substrate itself induces a strain in the film, which in turn degrades the quality of the film. So potentially we look for processing methods that use low temperatures, and one of them is plasma enhanced physical vapor deposition, also known as reactive sputtering. And advantages of reactive sputtering are that we get a better control over the flux of the active species. The global gas temperature or the plasma temperature is almost maintained at room temperature, and we use non-toxic gases. The system is much less complex and does not use ultra-high vacuum systems. And since it's simple, it has the potential for industry scale-up. Focusing on the reactive sputtering technique itself, we have at PICM, we have custom-built plasma reactor where we use liquid gallium as the target, argon as the sputtering gas, and nitrogen as the reactive gas to deposit gallium nitride. And the focus of this PhD is split into two. First is the qualification of the plasma itself, as it's the only medium between the target that we need to sputter and the material that we need to grow. And the other focus would be on the material growth properties. Plasma qualification, we use three plasma diagnostic techniques to qualify or characterize the plasma. First is two-photon absorption laser-induced fluorescence. Here's just a diagnostic setup. And we use it to estimate the nitrogen atom density in our plasma. And here is the plasma, and we probe laser on the plasma. And what happens is the nitrogen atoms, which are in its ground state, gets excited, and the subsequent de-excitation produces a fluorescence from which we measure the nitrogen atom density. And here is just an example of the nitrogen atom density with respect to a variation in pressure. And similarly, we use microwave interferometry to estimate electron density, and optical emission spectroscopy to analyze various processes, such as monitoring the sputtering of gallium, identifying any contamination in the plasma, such as oxygen species, or even estimation of gas temperatures. Focusing on the material qualification, we analyze the growth of gallium nitride in terms of composition, morphology, and structure at room temperature, and also further focus on the thermal series, where we increase the substrate temperature and see what happens in terms of crystallinity and other characteristics. So overall, we produce polycrystalline gallium nitride at room temperature, and we have some preliminary results on what's happening at higher substrate temperatures, where we get a better crystalline quality. But the idea is that we investigate the growth properties at each process parameter variation, and then kind of correlate it with the plasma characteristics in terms of density and temperature that we get, and then analyze the mechanism behind it to see what happens. That's it. Thank you.